Let's take a look at Euler circuits and paths. Let's start with our definitions. An Euler path uses every edge in the graph exactly once. An Euler circuit uses every edge in the graph exactly once and begins and ends at the same vertex. To help us decide which graphs have Euler paths and which graphs have Euler circuits, we have these three theorems that are going to be really helpful. The first one says a connected graph with at most two vertices of odd degree has at least one Euler path. When a graph has exactly two vertices of odd degree, the Euler path will begin at one of the odd degree vertices and it will end at the other. A connected graph in which all vertices have even degrees has at least one Euler circuit. This means that a graph with any odd degree will not have an Euler circuit. Okay, so again, what does this say really quickly? It says all even has an Euler circuit. It says if there are exactly two odds, there's an Euler path. Don't be confused here. You can have an Euler path with no odd degree vertices. So if it's all even, it's going to have an Euler path and an Euler circuit. If it has any odds, it can only have two to have an Euler path. If it has more than two, no Euler path, no Euler circuit. Let's make this clearer by doing some examples. So let's look at this graph. Does it have an Euler path, an Euler circuit? Does it have neither? Does it have both? Well, the first thing we should do is find out the degrees because all of the theorems talk about the degrees of the vertices. So I can see my degrees here are 3, 5, 3, and 3. Okay, so having odds says it doesn't have an Euler circuit. Having 4 odds, which is more than 2, says it doesn't have an Euler path. So why do I show you this as the first example? Because I want you to show you that this is the first example Euler had too. This is the graph that Euler came up with when they sent him that bridges problem. The bridges, remember we had all the bridges and they were trying to figure out could they go on a Sunday stroll, starting at one bridge, going through all the others and coming back to where they started. Turning everything into this graph that Euler made up and then him coming up with the theorems helped him answer the question, and the question's answer is no. You couldn't go on a stroll going over all the bridges and coming back to where you started without repetition. So they would have to repeat if they're trying to accomplish going over every bridge. So let's look at some that do work. So let's start here where I give you these three graphs, graph 1, graph 2, graph 3, and let's go through them and decide, are there Euler circuits, are there Euler paths, are there neither, are there both? All right, so easiest way to do this would be to write on here what's the degree. So here E is 2, A has 1, 2, 3, 4, B is the same, it's also 4, D has 3, and then C has 3. Okay, I have 2 odds. 2 odds says there's an Euler path, there's not an Euler circuit. Same thing here. A has 4, B has 1, 2, 3, 4, 5, it's a big one. C has 4, D has 3, I'm just going to write a 3 on top of it. E has 3, F has 4, and G has 3. Okay. I have 3, 3, 3, 5. There's 4 odd degrees, which says no Euler circuit, no Euler path. Okay, last one. A has 4, B has 2, C has 4, D has 2, E has 2, F has 4, and G has 2. Okay, all even this time. All even says yes, there's an Euler circuit, which means yes, there's an Euler path. So let's take some time and just look at Euler paths by themselves first, and then later we'll look at Euler circuits. So let's look at this graph, and I want to find an Euler path. Okay, first thing first would be let's break down the degree of each vertex. So I wrote them out for you. A is 3, B is 2, C is 2, D is 2, E is 1. All right, what that says to me, I need to look at the odds. A is 3, E is 1. So I need to start at an odd, and I want to end at the other odd. So I know I'm starting at either A or E. Just to make it simple, let's start at A. So let's say I start at A, and I need to kind of go around the shape before I go out here to E. If I go out to E first, I'm stuck because I've thrown myself kind of out here on an island. So instead, let's complete this look. So I go A, B, C, D, A. So I went all the way around, and then I can go over to E. So that would be one Euler path that I could come up with. A second one, instead of going to B first, I could go to D first. I could go A, D, C, B, A, and then over to E. that works too. So I've gone through every edge exactly once, and you can see when I'm drawing it, it's like I'm drawing the shape without picking up my pencil. That's what you want to look at for Euler paths and Euler circuits. Could you draw the shape without picking up your pencil? If I had started at E, I gave you two that if you wanted to, you could see, yeah, same thing. I would just go backwards from E. I would go around in either direction. So those two are there for you if you want them. All right, let's make it bigger. So here I gave you this graph, and I said, well, let's find an Euler path. Same thing I should do every time. I should say, well, let's look at the degrees of each one of them. So I can see this is 2, 2, 3, 3, 2, 2. So the 3's, that's where I want to start. So I'll start at C and end at D, or I'll start at D and end at C. So I chose, how about we start at C? All right, so if I start at C, I could go C, A, B, C, go across to D, and then I could go E, F, D. So I crossed over the whole thing, and I didn't pick up my pen once, and I drew the whole shape. That's what I'm looking to do. All right, I was trying to see if we had another slide there. So I didn't write it twice, so let me erase this one. Erase all the ink and show you I could do it again. That this time I could have said, instead of going C, A, B, I could have gone C, B, A, C, over to D, down to F, up to E, and then down to D. So there is more than one answer. There's a couple more that we could do, two more that start with C. So there's not a prescribed answer every time. There are things, just make sure that it does what it says it's supposed to do. It's an Euler path. It should go over every edge exactly once. All right, so I want you to try. This one has the same number of vertices as the last one. It just has a different shape. And I want you to find two different Euler paths for this graph. Pause it, draw these out for me, then come back. Okay. So let me show you some examples of what I see. Well, let's see, I started at E. I could go EA, D, B, AC, B, E, C. So I started at E, I ended at C. I know it's going to either end at E and start at E and end at C, or start at C and end at E, because I'm looking from odd to odd. Look at this one that I did, and then look at the one underneath it. If you look at it closely, you'll see I just wrote it backwards. This is called a mirror image, and I wanted to introduce you to this phrase. Mirror image is like when you look in the mirror and the things say backwards. If you had a t-shirt and it said a word, it would appear backwards in the mirror because it just doesn't reverse. And that's the idea here, is if you just reverse the steps, you didn't really tell me anything unique, you just told me it backwards. So if you want something unique, here it is on the next one, I could go E, C, A, and then E, B, A, D, B, C. So I didn't just go in backwards order of the other one. There are, of course, other answers. Just always make sure when you're drawing it out or writing it out that you're using every edge at exactly once. So not at least once, it's exactly once. Okay, so let's move on to Euler circuits. And I just want to remind you of a few things before we start. So when we look at Euler circuits, I want you to remember Euler circuits begin and end at the same vertex and only exist in graphs with all even degree vertices. I also want you to note that all circuits are paths, so anytime a graph has an Euler circuit, it immediately has an Euler path. All right, so let's start small. Here's my little graph, and I want to find an Euler circuit, and for clarity, I'm just going to say let's make it begin and end at A. Okay, so as you're doing this, make sure you use all of the edges, because Euler always means edges. Use all of them. Okay, so here's one I see. If I go A, B, C, D, B, E, A. So I just kind of went along the outside. And so this one is like a clear step that I'm doing. Let's make it a little bigger. So here I drew a bigger graph for you. And I want, again, start and end at A just to make it easier for us. So I'm going to show you multiple answers to this one. So here's one. I could go A, B, D, C, A, D, F, C, E, and then back to A. So I went over every edge, and that's why I draw on top of it, so you can see all the edges that I used. All right, I'll show you a different one. Let's say I could go A, C, D, B, A, D, F, C, E, and then roundabout back to A. One more. Let's say this time I started that way with AE, and I went CA, then I said D, CF, D, B, A. Okay, so you try. Here's one more graph. I want you to find an Euler circuit, and just one this time, and I want you to start from A. Okay. Again, I know I'm going to have multiple answers. I'll show you a few, so hopefully you've stopped and you've done this. If not, stop it and do it, and then come back and let's look at it together. So here, I could go A, B, C, G, F, oops, I said it wrong, A, B, C, G, B, I said F too soon. Here's F, then back to G, down to E, up to C, then D, E, F, A. Here's another one. I could go A, B, G, C, D, E, G, F, B, C, E, F, A. So hopefully you can see it traces and goes over all of them and goes back to the beginning. They don't always look pretty when I draw them, but it does show you how I used all of them exactly once.